Hello, and welcome to another episode of The Math Pete, I already started recording the episode. What is with all the racket over there?
Hey, Noah. I'm looking for some math.
What do you mean you're looking for some math?
Well, I'm looking for some math in an unexpected... Behold! The cube of Rubik!
I think it's just called a Rubik's Cube.
Behold! A Rubik's Cube! Noah, this may look like a familiar toy from the 1980s to you, and you are right, it is an awesome toy, but it is so much more than that.
Well, what do you mean by that?
I mean, it is chock full of very interesting mathematics.
Ooh, cool. Interesting mathematics. That sounds like it's perfect for episode 5 of the Math Club, Gleaming the Cube.
So, do you remember when this Rubik's Cube came out?
Yeah, absolutely. I mean, technically, I guess I would have to say I don't remember when it came out, because in doing a little research, I discovered that it actually was invented in 1974 when I was only 3 years old. But I definitely remember in the early 80s when it became a major craze. I was only about 11 or 12 years old, and I think every kid on the playground had a Rubik's Cube.
It's literally the only thing anybody wanted to talk about. You went out to the playground, and half the kids were on the monkey bars, and the other half were playing with some cube or one of the spin-offs, right? Like the Rubik's Pyramid or whatever it was called. And this thing went like wildfire, at least at my elementary school. It just swept through. But I will tell you this, I cannot remember a single kid being able to solve this thing. It was just too hard.
Oh, I totally solved the Rubik's Cube. I remember the day that I first solved it. Oh, absolutely. I remember getting a screwdriver and popping one of the corners off, and then very meticulously...
You know that's cheating, right?
But I solved it.
I guess we all do unexpected things sometimes, don't we?
Sure. Okay, granted. And in fact, actually, that's what you had to do if you ever wanted to get back to home base, right? You either had to figure it out, which nobody could, or pop them out, put them back in.
By the time I was done with this thing, those cubies were falling out left and right all on their own because I had loosened them so much.
It was so loose.
Yeah.
Okay, so I've got a thought experiment for us right now. I want to imagine, let's start with a cube disassembled. So all the little cubies are pulled out of it, and you've just sort of got the central axes, right, which look like a big sort of a plus sign. Now I'm going to ask you to reassemble the cube while blindfolded. So you do not get to look at what you're doing. You got to put it hold on and just put the pieces back in the order you think is best. And my question is, how likely do you think it is that you will solve the cube this way?
I'm going to guess, well, there's probably quite a few different combinations of ways I could put those cubies back together. I'm going to guess there's at least 24 different ways I could put those things together. I'm going to say 1 in 24. 1 in 24.
Would you believe that there are more than 1 million ways to do it?
More than 1 million different ways to put those pieces
together? How about
together?
More than 1 billion?
Okay. What's the actual number?
The actual number. You better sit down for this.
Okay.
519 quintillion, 24 quadrillion, 39 trillion, 293 billion, I'm still going here, 878 million, 272,000 outcomes to our thought experiment.
So that would be greater than 24.
A little bit, just, give or take.
Holy so did you start with 519 quintillion?
I did.
That is a huge number, Pete. So here's a question. How do I math this thing up to increase my chances of being able to solve this cube?
That is an excellent question. I just want to point out something. Holding a Rubik's Cube in your hand, it's roughly 2.5 by 2.5 by 2.5 inches, right? It fits very comfortably in the palm of your hand. Mm-hmm. And you are, in a very real sense, holding the number 519 quintillion. That is amazing, just because that is such an astronomically huge number. How do you wrap your head around it? Well, you kind of don't have to. You can just wrap your palm around it because it's sitting right in your hand, which is, I just think is something cool. But back to your question about using math. First, let's actually talk about how to arrive at the number 519 quintillion. Imagine holding the inner skeleton of the cube. And now let's look at the kinds of cubies that we have. There are really two types. There is the type of cubie that has 3 colored stickers on it, and those are the so-called corner pieces.
Gotcha. I remember that from my screwdriver days.
From your screwdriver days. And then the pieces that are in the middle, in between the corner cubies, are called edge pieces or edge cubies.
Right, and those have 2 stickers on them.
Exactly. Now, let me ask you this. How many edge cubies are there, and how many corner cubies are there?
Well, let's see. I would say that the front face, the one facing me, has 4 edges, and the back one has 4 edges, so that's 8, and then the 2 sides are going to have 2 more each. Is that going to be 12? 12 edges?
There are 12 edges. Good.
Okay.
Yeah, exactly. How about corners?
Corners, there's going to be just the 4 on top and the 4 on bottoms. That's going to be 8.
Exactly. Okay. Now, when we are thinking about building out the cube, let's focus first on the edge cubies. There are 12 edge cubies and 12 spots to put them. There are a total of 12 factorial ways that we could choose to put those edge cubies onto the main frame of the cube.
And to make sure I'm remembering this correctly, 12 factorial would mean 12 times 11 times 10 times 9 all the way down to 2, right?
Exactly. Yeah. And of course, you could keep going down to 1, but that won't change the value. You may have seen this written down, right, with an exclamation mark, 12 exclamation mark, and that means 12 times 11 times 10.
I always thought that just meant 12.
It's a very excited 12. And the reason there are 12 factorial ways is because you pick up one of the edges and you say, I'm going to put it here. You have a choice of 12 locations and you pick one of them. You pick up a second edge. You now have 11 places that you could put it. 12 times 11. That will count the number of ways to put those first 2 in.
I see. So and then 10,
all the way
9, and then 8, and then 7, until you put in the last piece, and it can only go in one place because it's the only place that's left.
Because there's only one place left. Now, I've actually hidden one choice that you also have to make for each of these 12 edges, and that's whether you're going to orient them, I sort of want to say, right side up or upside down. The white color above the green or the green above the white.
So is this 12 factorial times 2?
That would be if you only had to make one of the choices of orientation. But you have to do that for each of the 12 cubies.
Oh, my goodness. So is it 12 factorial times 24?
Almost. You're multiplying by 2, which was the right idea. So instead of multiplying by 12, for each of the 12 pieces, you want to multiply by another factor of 2. So 2 times 2 times 2 for a total of 2 to the 12. So just placing the edge cubies in, 12 factorial times 2 to the 12th. That's already a very big number. And we haven't even put the corners in yet.
Wow. And so now we're going to do the same thing with the corners, starting with 8 factorial times 2 to the 8th. Wait, no, because those corners can go 3 different ways, can't they?
They can. Because they have
so it's going to be 8 factorial times 3 to the 8th.
Exactly. The total number of arrangements that we can end up with here is 8 factorial times 3 to the 8th times 12 factorial times 2 to the 12th.
And that's how you get the 519 quintillion number?
That's 519 quintillion, exactly. Very economic way to write this down. Oh, in fact, you know what? I did this a couple of days ago. Listeners who have already heard prime time might enjoy taking that expression and writing down its prime factorization. I'm thinking about the fundamental theorem of arithmetic. You already know it's got numbers like 12 and 8 and 6 and so forth in it. It's not already in its prime factorization, but it's not hard to do. So I would challenge listeners to go ahead and do that.
I'm glad you're challenging listeners to do that instead of challenging me to do that right now while we're recording. I have a question. So out of these 519 quintillion ways that I might put the cube back together, if I were blindfolded and just started randomly snapping cubies back in, are all of those valid configurations that I could have gotten to if I hadn't taken all the pieces apart, if I had just started with a solved cube and just started scrambling it up?
That's an excellent question. Do you have a guess at what the answer is?
I'm going to guess that the answer is no, because I can picture a way that I could pop out just one cubie, flip it around, and put it back in. And I have now created a configuration that there wouldn't have been any way to get to by just rotating the faces of the cube.
That's exactly right. In fact, the odds that you will put together a configuration that is viable or valid is only 1 in 12. So for every 12 of these 519 quintillion arrangements, 11 of them are actually not valid. They are not physically realizable starting from a solved cube.
So the actual number of valid combinations is 519 quintillion divided by 12?
That's right.
And that probably gets us back down to around 24, right? My original guess.
You're off by a little more than 43 quintillion.
In the grand scheme of numbers, that's pretty close.
That's pretty close. Yeah, so the actual number of valid configurations is 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489 million, 856,000. That is a mouthful.
So still greater than 24 is what you're telling me.
Yep. So Noah, let me ask you this.
Okay.
If I hired you and said your job is to find a way to solve the cube given any one of these 43 quintillion starting configurations, how would you go about it?
Well, I gotta be honest, I don't know how I would go about it. I really think I would go look up a video on YouTube that shows how to start solving the Rubik's Cube.
Yeah, you just say, oh, somebody has solved this thing. I'll go ahead and solve it.
Right.
Well, you certainly would want to somehow find some shortcuts, right?
Sure.
For example, let's suppose that you said, Pete, I'm going to write a computer program. And let's say you made one that was blazing fast. It could solve a given configuration in a millisecond. So every millisecond, your algorithm could solve one of these positions. And that means 1,000 positions could be solved per second.
Right.
And now I'm going to be a little bit generous. And let's say I gave you a computer network so that you could distribute the work across multiple machines. And you were able to solve 1 million per second. Not just 1,000, but you could solve 1 million per second. How long do you think it would take to run your algorithm on all of these positions?
Well, if I can solve 1 million per second, it's going to be 43 quintillion divided by 1 million seconds. I don't know. Let's try to just put it into hours. 6 hours?
So you're off by a little more than 1 billion years. It would take you 1,371,512,026 years. It would take more than 1 billion years if you were able to solve 1 million positions per second. So clearly, that's not what we're going to do.
We're not going to brute force this.
We're not going to brute force it. And in fact, you may be wondering, how do we even know, going back to the original question, 1 in 12 of these positions is not valid? The answer is mathematics.
I was hoping it was going to be mathematics since this is the math club.
Yeah, if the answer was magic, actually, that would also be interesting. But it turns out that the answer is mathematics. So, as you say, to math this thing up, we need to start thinking systematically about the cube itself. That means we need to make some definitions. We need to talk about how we might label the different parts of the cube so that we can track them as various movements are being made.
So it sounds like we have to establish a few baselines right from the beginning.
Yeah, some conventions, right? And of course, there are quite a number of these out in the world. After all, people have been eagerly studying the cube since it first came out. But certainly by the early 1980s, people were writing books on how to solve the cube, how to think about Rubik.
Hello, my name is Rubik.
So let's use some of those pre-existing conventions so that we can tap into all of what the rest of the world has been thinking about. You've played with the Rubik's Cube. What are some things you think we're going to need to track as we are moving through our analysis?
Well, I guess the first thing that comes to mind is that when you rotate the face of a cube, you have two different choices of which way you're going to rotate it. You could rotate it clockwise or you could rotate it counterclockwise. So one thing you're going to need to keep track of is which way you're rotating it when you make a move.
Exactly. And which of the faces you're rotating.
Right.
Let's imagine that we've kind of got a fixed orientation in mind. Like we're staring at the orange face, and we're always going to keep the little face of the QB, the center guy, pointing at us. So now when I talk about which face to rotate, I actually can say which face relative to the fact that I'm holding the cube in this particular way.
And maybe we call them things like the front face, the back face, the left face, the right face. And then there's the top face and the bottom face if you're looking at a third axis. And then each one of those axes also has a center.
That's right. The center slice, the layer, right?
Right.
So I think we want to focus on the 6 faces that you named. And let's use just the first letter of the words that you said to refer to the faces. So F will mean the front face. So holding the cube in front of us, when we say F, we mean turn that face that you're looking at 90 degrees in the clockwise direction.
Got it.
We will use B for the back face, L for the left face, R for the right face. And now, instead of top and bottom, because then I would have to say bottom is B, but back is B, we will call the top face the up face. And so we will use U for that face and D for the downward face.
Okay, but I have to interrupt with a question now, because it's obvious when I'm looking at the front face what clockwise means and what counterclockwise means. But when I'm talking about the left or the right face, for example, what's clockwise and what's counterclockwise?
Great question. I was hoping you would ask that. We always mean clockwise as though you were looking directly at the face.
Got it.
So you mentioned that there's 2 choices. We can go the other direction, the counterclockwise direction. And the way we do that is very simple. We put a little apostrophe up at the top right-hand corner of each of these letters. That's if it were written down. I would say U prime for a 90-degree counterclockwise turn of the upper face, and so on, all the way around.
Got it.
Okay. So we have 12 different symbols, each corresponding to a move of the cube. F, F prime, B, and B prime, and so forth. So we've got 12 different moves. That actually turns out to be enough to completely understand what the cube is doing. We don't need to worry about the inner slices because we can arrange for those slices to be moved just by twisting the outer faces. Does that make sense?
Relatively. Sorry, what I mean is the inner slice is moving relatively by moving the 2 outer faces.
Yes. Yes. Okay. I was hoping you meant relatively in that sense and not you only relatively understand me because I'm talking gibberish.
I only ever relatively understand you, Pete, but let's keep going.
I know.
So I think I understand the notation we're talking about. Now, how do we use it?
How do we use it? To answer that question, it might help us if we keep this context in mind, but look at a radically simplified scenario that will allow us to think through the same concepts, but without so much motion and these very, very large numbers. Would you be on board with that if we talked about how about something really simple like a square?
Hey, if you're talking about something really simple, I'm your guy.
Okay. All right. So a square is a symmetric object, just like the cube is. The cube has a lot of symmetries to it. The Rubik's Cube itself has a lot of symmetry to it. As I move various faces around, sure, the colors on the front and sides and so forth change, but the overall structure of the cubies remains, well, essentially constant. If I took all of those stickers off and moved one of the faces, you would have no real way of knowing if I had turned the face or not, unless you saw me doing it, right? So that's an example of something called a symmetry, some geometric transformation that you can perform on an object without changing its apparent outward shape. So if you were to think about a square, what might be some of the symmetries you could identify with a square?
Well, first, let me make sure I'm picturing this right. Can I picture this as if I have a piece of paper that's cut out in the shape of a square and it's just sitting there on the table in front of me? And you're asking me what are some different ways that I could move that square that would be symmetrical moves where the square would look like it was in the same configuration after I moved it than it was before?
Exactly. In fact, I would like you to think of everything you can do to a square that would leave its appearance unchanged.
Well, I could only think of two things that I can do to a square that would meet that definition. One would be I could reach down and just rotate that square either 90 degrees or 180 degrees, or I could pick the square up and flip it over and put it back down so the other side of the square is now face up. So I think those are the only two things I could do where after I made the move, it would still look like the same square I started with.
Yeah, rotations and a flip. And if you allow yourself to combine some arbitrary number of each, rotate, rotate, flip, rotate backwards, flip again, whatever you come up with, you will have described all of the possible symmetries of this square. Now, we have deliberately said, how can you move the square so that we cannot tell that something has happened to it? Now we actually do need to tell what's happening so that we can quantify what's going on.
So we need some sort of equivalent to what the colored stickers on the Rubik's Cube would provide. So that when you rotate a face, even though the cube itself looks like the same 3x3x3 cube, the colored stickers indicate that you've made a rotation.
Yeah, exactly that. Now, instead of using colors, what about numbers? Let's write some numbers down on our square. There are 4 corners, so I will propose writing 1, 2, 3, 4 in that order, going around the square in the clockwise direction. In the upper left corner, I will write 1. In the upper right corner, I will write 2. In the lower right corner, I will write 3. And in the lower left corner, I'll put a 4. So now I've got 1, 2, 3, 4. And since we need to flip the square sometimes, I will flip the square over and write the numbers 1, 2, 3, 4 so that they correspond to the same ordering that they had on the original sides.
So the one corner is going to be the one corner regardless of which side you're looking at.
Yep, that's the idea. Now, when we put that square down and move it, we can see that the numbers have changed position relative to the home base position of 1 in the upper left, 2 in the upper right, 3 in the lower right, 4 in the lower left.
Oh, I see what we're doing. This is, just like you said, it just took me a minute to get there. This is a simplified version of what we can do with the Rubik's Cube and all the different ways we can twist and turn it around.
Exactly. And the numbers, in particular, the change in these numbers between a starting position and a final position is how we will measure which moves have happened. And if we are careful in the way we study these movements, we will be able to use just the labels themselves as representations of the geometry of these movements. And in doing that, we leave the world of geometry and enter the world of algebra. And this is a very beautiful and accessible entrance into the theory of groups. The Rubik's Cube gives us an example of a group, which is a certain kind of mathematical structure, but it's big and it's complex. The square, on the other hand, gives us a much smaller group that's actually very friendly and easy to understand. So we would want to argue by analogy. Well, it works this way for the square. Maybe it works similarly for the cube. And that would be the idea.
That makes sense.
What we end up with, if we write each of these numerical combinations, the ones that track the different geometric movements that we make, we end up with 8 different combinations. So, for example, 2, 3, 4, 1 would indicate a 90-degree rotation in the clockwise direction. So if you assemble all of these possibilities, you end up with 8 different sequences of numbers. Each is a permutation of the set 1, 2, 3, 4.
Boy, I sure am glad that we're doing this with a simpler example because my head is already starting to swim. I can only imagine how this group theory gets more and more complicated and complex as you now apply it to the cube instead of to the square.
Yeah, and not just to the cube, to Rubik's Cube. right? Because it is very complex with all of its quintillions of possibilities. So all of the results that are available to us in group theory apply to the Rubik's Cube group. And yes, it is a group that has 43 quintillion elements, but that doesn't mean we can't study it. And mathematicians have really broken down the structure of the Rubik's Cube by looking at it through this lens of group theory.
That's really fascinating, Pete. And it just goes to show that there is so much more going on with this puzzle mathematically than I ever thought when I was 12 years old on the playground twisting this cube around.
Oh, completely. That was the last thing on my mind, right? And that's why we were looking for mathematics in unexpected places. Here it is, playing a role in solving the Rubik's Cube.
Well, all of this brings me to what I think was the first question that popped into my head when we decided we were going to do an episode on the Rubik's Cube. Can all of this math and all of this group theory actually help me to solve the Rubik's Cube when I have it in my hands?
You know, look, if you want to solve the Rubik's Cube, go hop online. There are tons of excellent videos where people will walk you through it. And I've already seen a lot of friendly folks giving really good instructions. You know, the mathematical analysis, it does help, but it helps in a subtle way. For example, suppose I want to know the answer to this question. Given every possible configuration of the cube, what is the worst case scenario in terms of solving it? What is the hardest position to put it in? How many moves would it take to transform it into its home base position?
Well, let me take a stab, because you've asked a couple questions like this and I have guessed way too low. So I'm going to say the most number of moves it would take is 5 million.
Would you believe 20?
Oh, come on.
Oh, I love it. You walked right into that one. So this number, which measures the maximum number of moves required to solve the cube, has a name. It is called God's number, although I prefer to think of it as Gazoo's number in honor of the great Gazoo.
I like your idea better, my dear dum-dum.
This number attracted many, many people. As soon as mathematicians got their hands on the cube, they wanted to answer questions like, what's the worst case scenario? How can I find an optimal solution? What is the average number of moves it would take given an arbitrarily randomized cube? That answer, by the way, is 18. So in 1980, we knew of a starting configuration that required a minimum of 18 moves to solve. It was known that no more efficient way existed. What we didn't know was that that actually was close to the worst case scenario, although that wasn't known for another 30 years. In 2010, there was a collaboration involving Google, a mathematician, a math teacher, I believe an engineer, and they spent 35 years of CPU time to determine Gazoo's number, and they came up with 20. Let me say one point of clarification. Gazoo's number, which is 20, does allow for 180-degree rotations. If you're only willing to accept quarter turns, in other words, 90-degree rotations, then that number is 26. Naturally, it takes a little more because you can't get 180 degrees in a single flip.
Gotcha.
So that is a fascinating story unto itself, and it took 30 years to solve it. So people have been thinking mathematically about the cube for a long time.
Wow. Thanks for the great explanation of all the mathematics around the Rubik's Cube, Pete. That was interesting. And speaking of thanks, we do have some people that we need to thank on this episode of the Math Club.
Indeed, we do.
We would like to extend our heartfelt thanks to all of our beta listeners, who are Kevin and Levi Corin, Pete Mullen, and Kevin Murphy. All of them have been instrumental in listening to our early episodes and giving us feedback and helping us to make this show better at every step of the way.
I'm so grateful for the four of them. In fact, to express my gratitude, I'm going to call you all my cubies. You are my little cubies. Thanks, cubies.
Pete, why don't you tell people how they can get in touch with us if they have questions or comments or would like to suggest topics for future episodes?
Absolutely. Please send us an email at mathclubpodcast@gmail.com, or you can reach us on Twitter. Our handle is @mathclubpodcast.
And also, if you've been enjoying this show and you have a math lover in your life or someone that you just think might become a math lover, please share the show with them. The more, the merrier. Also, if you're so inclined, we would love it if you would rate and review us on Apple Podcasts. Every one of those reviews helps to spread the word and helps to grow the Math Club family.
And so, to all 519 quintillion of you listening to this show, thanks so much. We're glad you're here.
And we'll see you next time.